Hello, everyone. Welcome to our second session on KnowWhereGraph. So while we are waiting for more people coming in here, I'm going to give you first an introduction of this session, the outline of this session. So first, this session is more about the technical side of our project, KnowWhereGraph. The goal here is we want to provide you some hands-on experience or hands-on instructions on how to get access to our KnowWhereGraph. And today we have 5 presenters, including myself, and we are just a sub-team of the KnowWhereGraph team that are coming from different institutions and different affiliations. Next slide, please. So here is an outline of what you're gonna you can expect from today's tutorial or today's 101 session. So first, I'm gonna give you an overview of our seed graph, which is really the backbone of all the tools that are that is going to be introduced in the later. And after that, my colleague Charlie will introduce you the semantics underlying the KnowWhereGraph, meaning we are going to introduce the ontologies developed in our project. And then my colleague Tommy will introduce you the several tools to interact with our knowledge graph. And then my colleague Anthony and Rushi will give you an introduction or instruction on how to use the Geoenrichment tool that we developed to directly access our graph. And at the end, we are going to also introduce you how to use our graph via Python. And at the end, we hope you can we hope you have some questions or suggestions or comments to us to help us improve our project. By the way, all those materials we are going to present today are all listed in our GitHub page. And if you scroll down to this page here, you will find there are several links. And these links provide you more information about all today's materials. You can check it by yourself, or and if you have questions, feel free to email us or contact us. Can you go back to the slides, please, Charlie? All right, so first a little bit about what is KnowWhereGraph and what is the landscape of this seed graph. So our project actually is mainly motivated or designed based on 3 use cases, including direct relief, which is mainly focused on the humanitarian relief applications, and also farm to table and farm credits, which are mainly focused on the agriculture side of the project. And by working with all these different partners, different collaborators, our goal here is to help them to answer questions, include all those here, I listed here, including like where to allocate resource in response to Hurricane Katrina, and which farmland will be or has been already impacted by the oak fire that is currently happening in California, and when will those impact be, and how will it influence the supply chain from the farm to the tables. And examples such as also where are the farmlands are, and whether they are healthy or not, and how could we value their values in terms of agriculture. So based on all these, applications and competition questions, next slide, please. We developed our graph, which contains about over 20 environmental related themes, including data about climate matters, data about smoke plume, data about health, air quality, expert transportation, and so on. And as you can see, all these are different data silos. And our approach here is to use the space and time as the nexus to connect all these different themed silos. And while we're developing this, we also want other people to use it. So while we're developing them, we are trying to use all the standards developed by W3C and OGC. And the key ones here are SSN, the Semantic Sensor Network Ontology, the Time Ontology, and the GeoSPARQL, so that we want to make sure that our data, our graph can be integrated with others as well. Next slide, please. And so far, our data collected from multiple data resources. And here is a snapshot of all these different data resources and their spatial and temporal scopes. And as you can see, our data collected from like USDA, NOAA, USGS, FEMA, and the Department of Transportation, and so on. And for now, our project, our graph mainly focuses on the US. But in the next stage, actually, what we are doing now is actually we want to extend it to the globe as well. And you can check this table in our official website as well. Next slide, please. And to give you an overview of, what currently, what is the scale of our current knowledge graph, here is a table we generated. We are using an agile approach to develop our graph, meaning that we are having keep adding new data or keep developing new schema, and our graph evolves with new data added in, and we have different releases. So far, we released our first one, which is called the Vienna release. And in this version of KnowWhereGraph, there are in total about 12 billion statements about the environment, about the places, about the agriculture, and so on. And in total, we have about 689 classes and 214 properties. And we have over close to 2 billion headers and about like 1 billion regional identifiers. And this covers about like 2 billion in temporal instances. And we also included about 6,000 experts. And we are actually working on our next release, which will be called KnowWhereGraph Manhattan. And it will include more denser data and more robust schema. And we look forward to it, and we expect it to be released in the very, very near future. Next slide, please. And as I mentioned, the regional identifiers is really the nexus to help us connect all these different themed data. And so far, we consider over 8 different types of place or regional identifiers. And here we have a table listed all of them, and we listed the number of instances and a number of statements here to give an overview. And these identifiers so far includes the national weather zone in US, the federal judicial district in US, the marketed area in US, the zip code area, the census metropolitan area, and the climate divisions. We also use the S2 cell, which is global hierarchical grids, to help us integrate all these different place identifiers as well. Next slide, please. Okay, so now I will pass it to my colleague Charlie, and she will give us more overview on what is ontology looks like in our project.
Thank you, Ray. Hello, everyone. Now I will talk about the KnowWhereGraph ontology, which forms the semantic backbone of our KnowWhereGraph. The overall design of the ontology follows a 3-tiered framework. Going downward up at the lowermost level are the dataset ontologies, which contain the classes, properties, and named individuals corresponding to each individual dataset. At the next level, we have the taxonomy ontologies. These are derived from taxonomy hierarchies that provide a general and standardized typology of concepts in a domain. In KnowWhereGraph, we specifically use the hazard classification or the HIP classification developed by UNDRR, that's the United Nations Office of Disaster Risk Reduction. Finally, at the topmost level, we have the standard W3C ontologies on which both our dataset and taxonomy ontologies are grounded. The ontologies that we specifically use are GeoSPARQL, SOSA SSN, OWLTIME, SCOS, and QUDT. Overall, as Ray mentioned, our ontology contains 689 classes, 96 object properties, 118 data properties, and 325 named individuals so far. The entire ontology is constructed in a 3-step process. In the first step, for each data set, we draw out a schema diagram using the attributes extracted from the structured representation of the data. We use the wide editor for this purpose. In the next step, we translate the individual schema diagrams into ontology files in RDF format. Finally, we integrate all the individual RDF files to generate the integrated KWG ontology and verify its validity using reasoners within ProtoG to make sure that the ontology is free of any inconsistencies. The integrated ontology is finally loaded with the data into the graph repository to enable querying, reasoning, and inferencing on the data. Key to the design of all the dataset ontologies is the use of standard ontologies as a reference framework. I'll now talk briefly about how we do this using the SOSA ontology as an example. The SOSA ontology contains a set of core classes and properties for modeling observations, the entities that are observed, and the instruments that are used to measure these observations. So we have the observation and the observation collection classes that are linked to a specific feature of interest. The observation result can be denoted using the result class or using an RDF literal with the property has simple result. Each observation corresponds to a specific observable property, and the observation is made by a sensor that could be hosted on some instrument. Now, this source of feature of interest is the object whose properties are being measured, and it could be any real-world geographic phenomenon, such as a feature or an event. Now, this is an example of how one of the data sets, that's the EPA air quality data set in KnowWhereGraph, is modeled using SOSA. So we have the air quality observation collection, which corresponds both to a specific type of air pollutant. We have 8 different kinds of air pollutants, and each observation collection also corresponds to a specific air quality sensor and instruments that measures this. Each collection in turn has individual observations with different values at different time instance. Similarly, we also use other standards such as GeoSPARQL for modeling geographic features and their geometries, and the OWL-time for modeling temporal information in graph. This is a very high-level overview of the spatial model that is used to represent and connect all the spatial data sets in KnowWhereGraph. This may be a little bit easier to comprehend for folks who are familiar with GeoSPARQL, but if anyone else has questions, please feel free to ask at the end of this session. So we have here a set of KWG counterpart relations or object properties for each of the 6 RCC relations in GeoSPARQL. These 6 spatial relations are generically represented using the KWG spatial relation property. S2 cells are then modeled as specialization of the geospatial object class, whereas all the other spatial data sets, that's point, lines, and polygons, are denoted as a region, which is in turn a geofeature. Now, all the regional identifiers that Ray mentioned previously in his talk, also called as place identifiers, are individually related to administrative region and S2 cells using the spatial relation property. In the current release of our graph, we have all these relations pre-materialized as triples in the graph for more efficient querying capabilities. This schema here shows how space is now used as a nexus to link hazards and environmental observations in our graph. So as you can see here, we have our core hazard class, which is both a feature of interest as well as a feature linked to administrative regions and S2 cells using the 6 types of spatial relation properties. Likewise, observation collections, which are linked to SOSA feature of interest, are also linked to these 2 place identifiers. In a similar manner, we also have sensors, which are located in specific regions, linked to administrative regions and S2 cells. When I say linked, I mean that these are pre-materialized triples in the graph. With this, I will now pass over to my colleague Thomas, who will briefly talk about how the ontology and the different classes are used as facets to explore and navigate through the graph.
All right, so now that you've seen what's in the graph, how it's connected, we're going to shift over and start talking about how you can interact with this and how you can obtain this data. So there are 3 different ways to view, search, and obtain data in KnowWhereGraph. The first is using the Knowledge Explorer stack, and this contains a search interface and a dereferencing service. The second is using the Geoenrichment tool suite, and these are plugins for QGIS and ArcGIS, and these allow for a more traditional user experience for somebody that's more familiar with geospatial analysis. And then third, you can always query the SPARQL endpoint using any language of your choice. You can process these results, and this is for more advanced use cases, such as federated querying, custom visualizations, or integrating with your processing workflow. Next slide, please. So starting with the Knowledge Explorer, it's split into two web applications, and the first is the faceted search. And this provides a search interface to the graph database, and it was designed to fit the direct relief use case. So in that light, it focuses on places, hazards, and experts. The second half is our fuzzy link application, and every subject in the graph has a URI that can be visited as a hyperlink. And if you view this in the browser, you'll get a nice HTML rendering describing that particular node. Or you can also request the content type as RDF XML for more automated querying. And next up, we're just going to show a quick overview of the functionality of the faceted search. Next slide, please. Here we have the main landing page for the Knowledge Explorer. If you want to check out the site after this presentation, be sure to take a look at the step-by-step examples. As mentioned, this interface is primarily concerned with searching for places, hazards, and experts. We'll start by exploring places. On this tab, we can see a list of facets are given on the left-hand side, used to narrow down search results. The results are shown in the center, and a map displaying the location of each result is shown on the right. The Places tab allows users to explore and search for geographic locations. For example, you can search for man-made things like airports, buildings, or river crossings. The facets below allow users to search for administrative regions, zip or FIPS codes, climate divisions, and even national weather zones. The Hazards tab shares a number of facets with the Places tab. These allow you to search for hazards that happened in a particular area, or for hazards that occurred at a given feature type. For example, now we can search for hazards that shared a location with an airport. Here we see a hail event in Harris, Texas. All of the items in the table are clickable. These bring you to Fuzzy Link, where you can see a more rich description of each item. In this case, we can see more information about Harris. Zooming out, we can see exactly where it is in Texas. Zooming in, we can see that it has a distinct geometry. Scrolling down, we can see more properties. For example, we can see all of the different features that it contains. The next place facets allow you to search for hazards that happen in particular areas. For example, hazards that happen in a particular zip code area or FIPS code area, etc., etc. You can also constrain your results by different time frames with a start and end date. And last but not least, you can also narrow down your search for a particular type of hazard. In this case, we're going to explore the NOAA hazards, and these came from the NOAA data set. So we can see that it contains tornadoes, high wind events, flood events, etc., etc. There are also additional properties of these hazard events. So you can also narrow down your search results based on injuries or deaths. And scrolling up and taking a quick look at the results, we can see an avalanche, hail, a couple thunderstorms, and some very cold weather. The last tab is the People tab, and this lets you search for people that are experts in a particular field. And the facets on the left are used to narrow down the expert topics. For example, we can search for people that are experts in anthrax or cancer. In this case, we have two experts that have an expertise in both. And viewing more information about a particular expert will show you all of the different publications that they've been involved with. And you can in turn explore each of these publications even more. In this case, you can view its publication year, its location on the web, and a little more information about it. So together, these three tabs make up the faceted search and its integration with Fuzzy Link. And this concludes the demo of the Knowledge Explorer, and be sure to visit it at knowwheregraph.org. So next up, Anthony is going to introduce the Geoenrichment tools and go over the plugin for ArcGIS. Here we have the main landing page for the Knowledge Explorer.
Alrighty, thank you, Thomas. So today I'm going to be showing off a demo of the ArcGIS plugin so that you can see how we integrate our graph data into the application. So let's get that started. So here we're going to open up the tool itself. So we have our custom UI, and the first piece of information the user can provide is an area of interest to search. We have a blank map right now, so the user doesn't have any live layers to provide. We provided a few tools to expand options for the user, including the ability to draw a polygon and the ability to open a geodatabase file or shapefile in order to import a polygon. So right now we're going to draw a custom polygon right around Santa Barbara and just see what we can find in the graph in that area. So we search the new area we drew, and then we can begin exploring content. So the user interface for this particular tool, we wanted to kind of maintain some of the semantic web language and feel when browsing data. So the first thing we did when we searched this area was look for a list of geo features that were in this area. And if we pull down that list, we have a bunch of different things. And in this particular demo, we're going to look for wildfires that occurred in this area. We can also find out properties associated to those entities, just like you saw in the Fuzzy Link application in the Knowledge Explorer. And so in this particular case, we're going to grab just a simple one like the fire name. So it's hard to see that string right now, but that string says literal data found. So we've reached a point where we've run into some sort of textual or numeric based value. So we know that we are getting physical data that we can bring into our graph table. So of course, we bring the fire name in there. We have the option to relabel that if we choose. We're also given options to merge data. So if you're in a case where you're expecting multiple text or even multiple numeric values, we can get that information back. So you could do things like averages, standard deviation, or just concatenating string data. We won't show any of those particular examples in this demo, so we're just going to leave it at the default. We can go back to the select content window and continue searching for more information about wildfire. In this particular case, we're going to look for when the fire occurred, specifically the date. And so just like in semantic web, following the OWL standard, we're able to get to a temporal entity, and we're able to find the physical date information about wildfires in that area. So once we get the particular information we want about an entity, in this case, our wildfires, we can then, sorry about that. We can then actually add that layer to our ArcGIS application. All right, so we're back back here. So we will give our layer a name. And then that will go through and create a physical layer in ArcGIS. In this case, we get a polygon layer representing all the fires in that area. And if we open the attribute table for this layer, you're going to see some basic information from the graph, including the URI to the entity, as well as the name and date that we asked for from the graph content. If we click on an individual polygon, you can see that specific row. And if you click on the URI, it will actually launch you into the Knowledge Explorer that Thomas, pun intended with the fire name, presented earlier. So we can also continue our search in this area and look for other things. So we're going to start a new example, and this time we can reselect our layer. That's going to search over it again, and then we're going to, at this time, look for hospitals in the area. So we're going to get some information about those hospitals. So we will start off with a simple address, so we know where the hospital is. And we can continue to add content. Next, we can look for something like phone numbers, maybe if we wanted to get in contact with the hospital, or just have that information. And then the last thing we're going to look up here is, for fun, whether or not a hospital has a helipad. So as you can see, following the semantic of it, we run into this entity of helipad availability. We click explore further. Sorry again. And when we click explore further, this is just simply us continuing the chain that you would expect in a semantic web context of entities and properties. So we get the helipad availability. As you see, the label isn't the most helpful name, so we'll switch that to helipad access. And we're going to save this layer. And so now in this particular case, it's going to build a map point layer that represents 4 hospitals that we found. And we'll zoom in on those. And of particular interest, there's a hospital that occurred near the edge of this fire. So we have all the information we requested, the address, the telephone number. And so let's look at that hospital, and we see we found the Santa Barbara Psychiatric Health Facility. And then we click on the fire, and we learn that this was the paint fire that occurred in the 1990s. So we, while looking for a particular interaction between the two objects, in this case, we found that this fire happened a while ago, and it might not have a direct effect on this particular facility. But you could see the case where, if you have a hospital that interacted with a current fire, that you might find ways to use that information. And we're going to look at another object in the graph. In this particular case, we're going to look at road segments. And we're not going to look for additional information about the road segments. We just want the entities themselves. And we want to see how these fires maybe affected road lines leading to the hospitals. So we look at the attribute table. Again, we didn't ask for any particular additional information. So the table itself might not have information that we're looking for, but we can see that this fire did pass over a large major road section. And if this is an area that is susceptible to wildfires, it might be good to know that if you're trapped on that road, that a nearby hospital has helipad access. And so that's just a very simple example of looking for things in ArcGIS. I'm going to pass over to my colleague Rushi, who is going to share the same thing for QGIS.
Thank you, Anthony. So I'll be demoing the Geoenrichment plugin for QGIS. Once installed, this plugin can be found in the plugins section of QGIS application. So to run this tool, users can either select an existing polygon layer, draw area of interest using the polygon drawing tool, or browse files from disk. We currently support shapefiles and geopackage files to load into your project. Once a file is selected, all the existing polygon layers from that file will be loaded into your current project layer. We'll be covering the use case of fires and air quality sites in Los Angeles area. So we'll start by loading that layer into our window and start exploring contents from the graph. We'll see all the properties that are available in this area, and we'll select fire and retrieve the fire name associated with those fires from the graph and add that content to our main plugin window. Next, we'll retrieve the date timestamps associated with those fires. This graph traversal can be of more than 1 degree, like in this case of temporal scope. To do so, we can click on the Explore Further button to retrieve for more than 1 degree. Users have option to customize how they want to store this information into their project. So we'll go through all those options of storing that information and save that layer as fires in Los Angeles area. When we click on the Run button, we'll retrieve all the properties in that area and save that in a geopackage file. This attribute table shows all the fire entities from the area with the fire name and fire date attributes that we retrieve. We also have the option of selecting a specific entity to learn more about that entity. And we can use the link to go to the Knowledge Explorer tool to learn more about that particular entity. Next, we'll retrieve the air quality sites in this same area. So we'll load the same layer again and start exploring contents from the graph. This time we'll be selecting the air quality site as the feature and the site name as the property of that particular feature that we want to retrieve from the graph. We'll select that information, add contents back to our main plugin window, and store that as air quality sites in Los Angeles and run the tool. We can see that these point geometries have been added to our main project layer. This plugin is cross-platform compatible, so you can use any operating system that supports QGIS to run this tool. And now that we have seen how to use this tool for ArcGIS and QGIS applications, I'll pass over to my colleague Thomas to show you how to programmatically access data from the graph.
So there's nothing stopping anybody from using their favorite programming language to talk to the database SPARQL endpoint. And in this case, we're just going to download the point geometries for the path of Hurricane Katrina and we're just going to plot them and export them as a shapefile. To do this, there's a Jupyter notebook that's been pre-computed that we'll just briefly go over. And so in this case, we're using the SPARQL wrapper Python package to interact with SPARQL. The most complicated aspect of this workflow is crafting the SPARQL query. In this case, you can see that I'm leveraging the structure of the ontology to go and find the geometries of the storm tracklets. And storm track is made up of storm tracklets. And so next, we download the data, we put it in a data frame, and we use a geodata frame to plot this over the US. And here you can see Hurricane Katrina starting off the coast of Florida, coming up through the Gulf, and ending in the Northeast. From here, you can, of course, export this to a shapefile. You can include this in your personal workflow, whatever that might be. And this is just an example to work off of.
All right, thank you to our team for a very wonderful presentations of our tools and our data and ontology. And I know that we showed you a lot. We have so many tools and so many different applications here. And here is another reminder that all our materials presented here are available through this link. So through there, you can download all our plugins, you can check our instructions, check the examples, check the example codes, and we are open to hear your comments and your feedbacks, or if you want to collaborate, let us know. All right, so right now we are right on time. We have about like 8 minutes for questions. You can either type it in the chat, or you can just simply unmute yourself and speak up, please. Okay, so while we are waiting for more new questions and comments coming, we saw that in the comments, we have one question that is from Peng Yu, asking us about whether, let me see, whether all these events associated with synchronized sensor data. So actually, Yano responds a little bit here. I want to add more, which is that, you know, our data are from different sensors. For example, for one event, Hurricane Katrina, so it will have the attributes or have the observations such as impacts, how many people died there, how many properties were damaged there. We also have observations about, like, you know, how much money FEMA has sent the budget to this region. We also have observations about the local climate environment around that specific region. So we have all these different observations. They are collected from different sensors. So we use the ontology called the SALSA to try to integrate all these different sensors. And these sensors, they are from different data sources as well. And some of them are, as Yano mentioned, they are raw data. Some of them are actually more derived from some computations. Hope that answers your question. Now we have a new question. Jonathan, you can unmute yourself and speak up. Thanks.
Hi, yeah, my name is Jonathan Blythe. I work at the Bureau of Ocean Energy Management. And also I've been involved with the Earth Science Information Partners Discovery Cluster, where we just had a meeting. We were looking at knowledge graph integration between NASA and other federal agencies. And I'm really interested in the way that you're managing geospatial data through these graph databases. So I'd like to be like to learn more about this and maybe invite someone from your group to come present to us at ESIP. But my basic question is, what I may have missed this, but what I'm seeing is this is like a data access protocol, a way to get to the data. And is there a discovery layer? I mean, the way that we're looking at knowledge graphs is to support discovery across different domains. So is there like a catalog interface you can work through before you get to the data layers, or is everything handled through that, that simple GUI that takes you right to the data?
Yes. Thanks a lot for the question, Jonathan. We definitely looking forward to for further collaborations with you. Just send us an email. We will definitely bridge up our team and your team. So regarding your question whether we have some catalog so that people can jump in here. So Charlie stopped at this page. So first we have this Knowledge Explorer interface. From there, you can already actually check the major facet, or we call it facet here. There are actually major classes that are included in our graph. And maybe Charlie, you can also share the link about our ontology. From there, we can also have a catalog of the major classes we modeled or we included in our graph. That's my quick response to this. My team members, if you have more, please jump in here.
Yeah, as Ray mentioned, the Knowledge Explorer is, I think at the moment, the kind of biggest interface to viewing the data that's in the graph. In the future, we might generalize that a little more to include more classes and more general search features.
So maybe if I can add one more thing, obviously it's a good question, so everybody is keen on jumping in. So we have a full openly available query interface. So basically you can get in there and get all the data, but also get all the schema knowledge, what you call the catalog, so to speak, and then look up what is there, what classes have been used, how they are formalized and stuff like this. But we also have a documentation together with some examples how to write queries and stuff like this that would help. And we can also give you access to visualization tools that help you more easily explore the ontologies. That said, if you're more interested in the catalog, and if I hear you say catalog, I believe you mean like the number of classes and relationships, so the schema, the T-box knowledge, then there will be also a discussion about this by Kogen Shimizu and Pascal Hitzler later on or tomorrow. So that may be very interesting for you.
Yeah, great. This is good, and I'll look at these materials and send email to you guys to see where we could share ideas and collaborate.
Sweet, sounds good. Thanks. Okay, so we have 2 more minutes. While we are waiting for you, probably typing your questions. Here are a question actually previously mentioned to mostly Anthony and Rushi. Can you comment on the scalability of your developed tool? And has it been tested on other knowledge graphs that are, which is not KnowWhereGraph, that is mainly focused on environmental intelligence and places? Can you comment on that?
Yeah, I can definitely take this one. The scalability issues, obviously, when you're dealing with this many statements and just size of any data store, scalability, especially with a interface that's primarily over a web API, you just run into natural limitations with the web. Obviously, our demos today in the GIS focus on smaller city areas, but you can imagine as you scale up the area of interest to a state or even a country, you're dealing with a lot of data moving over the web. And so we're working on solutions to improve that and make that more efficient. One particular area of interest that has come up is we want users to be able to provide their own polygon data as a search input to find out, okay, I have this area of interest that I've been working on, what's in that area. And we found out very quickly that if those areas have very complex geometry with over thousands of points of geometry, we run into limits both on the web side, but then also on the physical query tool itself. And so we're working through those those limitations and seeing ways that we can expand that further. And then to go to the question really quick about testing with other graphs, one of the things we tried to do with this tool is really lean into, specifically with the user interface, is lean into just semantic web usage and really hard into that rather than specifically into the structure of the KnowWhereGraph. So one of the things developing as this tool, as the graph evolved, was we kind of had to adapt each time that the schema evolved in the graph as we got towards our first release. And so right now, the tool, the only query that's specific to the structure of our graph is actually that first query that goes out and finds the entities that are in there. But even that query was more done for optimization. We could easily make that a query that is more general to a GeoSPARQL based, RDF based ontology. So there's definitely potential for this tool to work with other knowledge graphs.
Awesome. All right, so thanks a lot, everyone. We are right on time, and thanks a lot for your questions and for participating in our session. Our next session, which will be more about the application or use case side of KnowWhereGraph, will happen in about 15 minutes in this same Zoom link. We will see you there. Thank you very much, everyone.